Welcome back, everyone, to the second science session of the day. This is a galactic extragalactic session, and we have Sylvia who's been kicking it off with some galactic side of things. Take it away, Sylvia.
Hello, everyone. So I am Sylvia. I'm a PhD student at Curtin, actually in the final 9 days of my PhD. We heard a lot about the MWA, and now we are going to move and see what it actually enables to do. Today I'm presenting a data release covering the galactic plane from the GLEMEX project. So the galactic plane is quite a complex and rich environment. We have many astronomical sources that we can explore, starting from stars, supernova remnants, H2 regions, pulsars, magnetic fields, filamentary structures. And in order to study all these objects, we need to survey the sky. We have done it multiple times with different instruments, with different techniques. And all those surveys differ in terms of resolution, sensitivity, sky coverage, and frequency coverage. A great example of the latest achievement is given in the slide, where you can see the meerkat view of our galactic center, where there are a lot of filamentary structures that we weren't able to detect before, and we actually don't know with certainty what they are or how they are originated. We are missing the details of the larger scales, as you can see, for example, from these big supernova remnants. So we are unable to detect the entire flux of these diffuse sources. So to move on, the sources that I mainly interested in, supernova remnants, of course, they are the final explosion when a star dies. And I study what is left over after this explosion. The shock wave that is originated expand in the surrounding environment until it becomes part of it after hundreds of thousands of years. They are dominated by non-thermal synchrotron radiations, which means that they have a negative spectral index, varies from -0.7 to -0.2, which makes them brighter at the lower frequencies. And they also have a quite wide range of sizes, from 1 arcminute to 5.5 degrees. There is a missing population problems with these objects. In fact, the theoretical predictions expect almost 2,000 supernova remnants in our galaxy, but we have only detected 350 of them. And one of the main problems is that we are missing the older and the fainter sample of these populations. And this is because most of the surveys have been focused in mid to high frequencies, where the sources can actually fade quicker, and they are not sensitive to the larger angular scales. So we are missing the bigger elements of these objects. Another source that I'm interested in are pulsars, which are rapidly rotating neutron stars, which are observed as periodic radio pulses. And every time the beam intersects our line of sight, we detect a pulse. They're also non-thermal sources with a mean spectral index of -1.4, so they get brighter at lower frequencies. But most of the sources have been detected at higher frequencies using pulsation searches, which are focused at the gigahertz, in the gigahertz regime, because they struggle at lower frequencies because of the effects of propagation effects such as scattering and dispersion. Also, in some of these, in the spectrum of some of these sources, there can be a curvature, and so the flux that we expect to detect is actually lower. To overcome all these issues, we decided to create another image of the galactic plane at lower frequencies, and we use the MWA, of course. We combine observations from the galactic and extragalactical sky MWA survey, or GLEM, that you can see here in the left part of the slide, which covers the whole southern galactic plane south of declinations plus 30. With the GLIM extended survey, which you can see instead on the right, we have two publicly available relays, DR1 and DR2, highlighted in the dark red color, and the final release will be available by the end of the year. The main difference between these two surveys is that they have been taken using two configurations of the array. In particular, GLIM has been observed using phase 1, which had a very dense core of short baselines with a maximum baseline of 2.5 kilometers. And these made the surveys quite sensitive to the larger scales, from 2 arc minutes to 15 degrees. But we had quite high RMS noises over the image, varying from 6 to 10 millijansky per beam in the extragalactic sky, and from 50 to 100 along the galactic plane. GLIMX instead was observed after the upgrade of MWA with the extended phase 2 configuration, which had a less dense core, with the shorter baselines now being 100 meters, and we expanded the longest baseline to 5 kilometers to improve the resolution. We can now resolve smaller scales from 45 arc seconds to 20 arc minutes, and we have much better RMS noises of 1 millijansky per beam. So it is already in the extragalactic sky, which is 10 times better than what we could achieve with GLIM. So we wanted to take the advantages of both these surveys. We wanted to being able to have the big picture that the GLIM surveys is able to give us, plus the fine details that instead GLIMX is able to resolve. And to do this, we use a pipeline, which is based on the GLIMX pipeline. We divided the sky into small groups, as you can see from the bottom right plot. Each square corresponds to a group composed of approximately 15-20 observations, in part taken from GLIM and in part taken from GLIMX. We have analyzed each one of those, performing quality assessments such as flagging, calibrations, etc. And then we have performed initial imaging, which enable us to save the position of all the sources and that we put on the side in what we call the LDM screens, that together with the beam of every observations went into the final imaging algorithm. For this, we used the image domain gridding implementation in WSCLIM. IDG is quite useful because it enables to correct for direction-dependent effects, such as the ionospheres and such as the different beam responses over the array. And these allow us to combine observations that were taken at different times with different array configurations. The results is shown in blue here in the plot. We covered the galactic plane from plus and minus 11 degrees in latitude and from 233 to 44 degrees in longitude. And we covered the frequency range from 72 to 231 megahertz, which was divided into 20 subbands. And the results is shown here in this video. To create the video, we have overlaid all the 20 subbands mosaics using a Gaussian weighting scheme. We have reached RMS noises that varies from 3 to 15 millijansky per beam, depending on the observing frequency. As you can see, when the galactic plane moves along, you can see a lot of the diffuse structures that are part of it. Here, that is coming the galactic center. Sorry, I think the video is too big and it's not handled properly. There are a lot of different colors, and I'm going to talk about it in a second. And now we're going towards the northern hemisphere, so it gets a little bit noisier. One of the big advantages of this image is the fact that we can observe the sources with what we call the radio color. So overlaying the images from the 20 subchannels, we can actually distinguish bluish and reddish sources, and this is given by the emission mechanism that is dominant. In particular, the red sources correspond to non-thermal sources, in particular supernova remnants, while the bluish sources correspond to thermal sources, which have their emission absorbed at the lowest frequencies. So we are able to distinguish what we couldn't see in the gray scale is that part of the thermal emission was interacting with the supernova remnants, or some structures that resemble the shape of a shell wasn't actually what we thought it could have been an ideal candidate. The first application for this release was the cross-match of the catalog with the ATNF pulsar catalog. We have identified 184 canonical pulsars and 10 millisecond pulsars. And as I mentioned, those sources are not explored, not too much explored at the lowest frequencies, below 400 megahertz, because of propagation effects. So the spectra are not well studied, but thanks to the image, we could perform spectral fitting across the 20 subbands, and we could combine those informations with the ATNF pulsar catalog. We used the pulsar spectra software developed by Swestone et al. In 2022, and we fitted the spectra using 5 different models, a simple power law, which is the most used one. And then we had a broken power law, a low frequency turnover, a high frequency cutoff, and a double turnover. We performed this fitting for all the 284 pulsars that we have detected, and we found that without the addition of the low frequency data, 54% of the sources are well fitted by a simple power law. But after the addition of the low frequency informations, this percentage drops by 30%, and most of the spectra now are well fitted by a low frequency turnover or a high frequency cutoff. So this is a great example how low frequency information can actually help understand how the spectra of these sources evolve. Thank you for your attention. I'll leave you with the video again, and here there is a QR code where you can buy a fantastic scarf with the image of the galactic plane. Thank you so much.
Great job, you finished early actually. Any questions for Silvia in the room? Ron to start, I guess.
Hi, Sylvia. This is really great. In your introduction, you showed the galactic center region, yep. Which is quite spectacular, especially because of all the filaments.
Yep.
Now, one question has been, is that just the galactic center, or are there structures like this in the rest of the galaxy? So would have you been able to pick that kind of filamentary structure?
I am actually not too sure. So the Mirka team have only produced such a high detail image of the galactic center. And we quite don't know what those filamentary structures are. So I'm not too sure if we can observe them elsewhere.
Ron, you might need to get a scarf so that you can see for yourself. Is this on? Yeah. So yeah, beautiful talk, Sylvia. You've mentioned that there's like 6 different kinds of spectral fitting that can be done, but I know that most catalog formats that are used for calibration will only support simple power law and a curved power law at most. If would it make sense to do you think calibration solutions would improve if there was models that took into account these other types of flux curves, like the cutoff, the high cutoff, and the turnover, and all of those things?
So you're asking whether the calibration for the observations will improve the fitting in the spectra?
Yeah.
That's a very good question. I think we were able to extrapolate the most out of the data. The improved resolutions of GLIMEX actually, in particular for the point sources, is enough to be able to get all the flux informations.
Thanks.
One from Gov.
Hi, Sylvia. A follow-on from that question. So by increasing the number of flux values at low frequencies, you found an increase at high frequency cutoffs. That was one of the things, the graph.
Yes, because most of the pulsars only had 1 or 2 data points, and so it was actually hard. Like we couldn't perform a fitting before, and with the addition of the low frequency data, we could actually see, we have more data points, and so you can fit the data.
Awesome, thank you.
Right, I'm going to ask a question because I've got something I want to ask as well. I'm quite interested in your experience in developing and then running a pipeline on so many observations for the image domain gridding. Did you find that most of them worked without a hitch, or do you have to go in and get your hands in the dough and like need some of them to make them work a little bit better?
I would say that I had to go through most of them and actually double check. There were errors for, I would say 99% of the groups. And I actually had to go there, verify, well, how was the image, what was the issue, and rerun the script. Yeah, it was quite, it wasn't very, how do you say, overflowing. Yeah, automated, thank you. That's why it took, 1.5 years to finish the whole.
Lots of effort,
Yeah.
and a lot of good effort, that is. If there's no more questions, I think we've got actually ahead of time a little bit. So can you thank Sylvia once again while you set up the next speaker? Next up, we have Susmita, who's also going to be within the plane of the galaxy, doing some pulsars. Take it away, Susmita.
Hello, everyone. Good afternoon. My name is Sushmita. I currently work in the operations team at SKO, but today I will be talking to you more about the work that I did in the last part of my PhD, focusing again on the galactic plane, very similar to Sylvia, but the only difference being we are using MWA VCS data. So initially, when we started out this little pilot survey, along with my supervisors, Ramesh, Marcin, and Emil, this was more about finding new and interesting pulsars and transients. However, as the progress of the project evolved, we realized that this was more about understanding and realizing the pros and cons of image-based searches using MWA VCS data and the limitations and the caveats one has to keep in mind if you're looking at the image domain, especially for pulsar science. So in the next 10 or 15 minutes or so, I will give a brief introduction following up from what Sylvia's talked about pulsars and the spectral fits of the pulsars, then moving on to how this project has developed over the last 3 years, mainly focusing on the image-based pipeline that we developed as part of the project, the pilot survey focusing on the galactic plane, and the initial pulsar census and the detections we get out of this work. And I will leave it with some future prospects and some of the great work that the Pulsar team has been doing in this term over the last couple of years. So one of the key questions that we aim to answer in the era where SKLO is up and running and is doing some great work already is that will low frequency image-based pulsar searches be important for future surveys, especially relating to SKLO? And hopefully by the end of this presentation, we will all unanimously say yes. And with the help of MWA and all of the pulsar work that we do, that will be beneficial for SKLO in the future. So I'm not going to go over this again, but as Sylvia pointed out, that pulsars are highly magnetized rotating neutron stars, which have two beams of radiation from the poles, which when sweeps across our line of sight, we see as pulses. These are really, really great labs for testing our general understanding of fundamental physics concepts in high energy and really high magnetic fields, and finding more of these will eventually help us understand the whole population of these objects and all of the little kinks and little important things that we can learn from them. So some of the properties of pulsars that we focus on in this work is mainly spectral index, circular polarization, and variability. However, in this talk, I will mainly talk about the spectral index aspect of these objects. So as Sylvia also pointed out, up until now, and even I think going from here, a lot of the pulsars and the new pulsars will eventually be discovered with periodicity searches, and before a lot of them, almost like most of them, have been discovered with the Parkes radio telescope using beamformed and periodicity searches, especially at gigahertz frequencies. They are really sensitive, and like I said, they led to the majority of pulsar discoveries. However, they lack in terms of computationally challenging, so it requires a lot of computational resources and time in order to do a lot of large, full like large field of view periodicity searches to detect these objects. On the other hand, we do have image domain searches, and those are less computationally expensive, and they are more likely to detect high DM pulsars, especially at lower frequencies, such as that of the MWA. However, given that we do not recover the pulse information of the pulsars itself, they are less sensitive than traditional searches. So that's one point that we need to keep in mind when we talk about image domain searches going forward. So as we all know, our favorite instrument here is MWA, and one aspect of MWA that I use in this work is the VCS, or the voltage capture system. And from now on, when I say VCS, it will be the legacy VCS data that I have mainly worked on. And so this is just a very quick summary of how the VCS system worked before when I started doing this work. You have all of the data that goes into the beamforming and all of the channelization, and then goes to POSI, and then you can use that data. So one of the things that I would really like to highlight is the advantage of using VCS data. So the VCS data provides maximum maximum data processing flexibility, and by that I mean the VCS data, or the voltages, can be processed using a beamformer to form tide array beam and do traditional pulsar searches. And to more about all of the great work that is being done with the help of the beamforming aspect of VCS, check out all of the talks that's happening in the pulsar session tomorrow afternoon. On the other hand, we do have the correlator aspect. The same VCS data can then be passed through a correlator to form images, or wide field of view images, using the MWA, both in both polarization Stokes I and V, which is useful for the work that I am doing, as well as some of the work that Christian, PhD student, is already doing. So this is basically the pipeline that we developed along with Martin and Ramesh and Emil as part of the PhD, which was mainly taking the raw VCS data, offline correlating it, and finally going through all of the steps to create full Stokes images for all of the 60 or 90 minutes of data. So all of those stacked images were highly useful in generating source catalog and then going forward with a lot of the pulsar census work that we were aiming to do. On the other hand, the 1-second images that we produce would also be helpful in doing a lot of the variability studies of the pulsars itself. So taking all of that, we wanted to do an image-based galactic plane survey using the MWA VCS data, and we chose 12 observations that covered majority of the galactic plane. There were 12 MWA phase 2 extended observations with a sky coverage of about 6,000 square degrees, and the total amount of data that was processed as part of this pilot project was about 450 terabytes of legacy MWA VCS data. And one of the questions that we were aiming to answer is, focusing on the galactic plane, is image-based pulsars detection performing as good as periodicity or beamformed searches? So this was the initial methodology, and this was mainly because this had to be done in a certain period of time, given that that was part of my PhD project, as well as the fact that we had limited computational resources. So we decided to choose a control sample or a smaller sample of pulsars that fit in that galactic plane to do all of our analysis on. So we started out with 4,300 pulsars approximately in the ATNF catalog, and then around 1,000 of those pulsars were in the primary beam of the data. And then we took the local RMS values at those positions of the pulsars, and we told that a detection will be considered a detection if it was 5 sigma above that. And that got down to almost like 85% of those 1,000 pulsars were below our detection limit at the time of the images that we were producing. Given that it was in the galactic plane, another thing to consider is that a lot of the pulsars would actually reside in a supernova remnant that Sylvia's interested in, or in pulsar whale nebula that the rest of the pulsar people are interested in. However, from the imaging aspect, they wouldn't really be detected as a pulsar, but just as a radio continuum source. So we had to discard all of the pulsars that were in such environments. That brought us down to 110 of the pulsar samples. And this, you can take this as just a very summary slide of all of the detections that we got. So out of those 110 pulsar samples, 17 of them were detected in beamform searches only, whereas 16 of them were detected in image-based searches only. And image-based searches mainly included exploring the properties of the pulsars, comparing them to the known properties of those pulsars, and cross-matching with the ATNF catalog. On the other hand, we had 50 of the pulsars which were detected in both beamformed as well as image domain searches, leading us to a total of 83 pulsar detections in the pilot survey. And all of those, out of those 83, we had 3 MSPs and 4 binary pulsars. And for 14 of them, we have the first low frequency detections ever reported. So this is just a pictorial representation of all of the pulsars that was detected in this survey. And if I project this onto a different plane, just to try and understand, is there any particular section or is there any particular advantage of using image-based searches? And this is a very, very naive and crude approach, I have to say. So if we project it on the flux density to a DM plane, we can clearly see that the image-based searches are hitting a portion of that plane, which is unique to images only. So there is a lot of pulsars in this survey that is only being detected in image domain searches and not in beamform searches. And in the next few slides, I'll go through a couple of the examples. Just to point it out, a lot of the image domain search detected pulsars are mainly the ones that have really high DM. So when you go down to lower frequencies, such as that of MWA, due to the DM and scattering and propagation effects, a lot of these pulsars are very hard to detect at any frequencies less than 300 megahertz. And that is where the image domain searches come into play. On the other hand, we also have a lot of pulsars that's only detected in beamform searches in this pilot survey, and that's because they are completely below the detection threshold or the sensitivity threshold of the images that we are making. So this is one of the interesting detections that, interesting pulsars that were detected in both. So it's a binary pulsar with a white dwarf companion, and they were detected in both imaging and periodic searches with comparable significance, which is a tick mark for our pipeline and for our analysis. Moving on, we have only a time domain detection, which means that it was only detected in periodic searches and not in imaging. And that was potentially because it was below our detection threshold for that one particular image for that observation. And then we also have one in imaging, and this is quite interesting. In the top panel, you can see the MWA detection. That is the one that comes out of our work. And below we have the same source position in RACS, which is the ASCAP survey at higher frequencies. And what we can see is the profile that we get out of MWA just looks like RFI, so there's no detection. And that's because the profile, that the integrated profile gets really scattered at lower frequencies, and therefore it's very hard for us to detect it. So that's a binary with a main sequence star companion. And this detection was mainly missed by periodic searches because of the high DM that it has and its highly scattered profile. So like Sylvia mentioned, the advantage of doing image-based pulsar searches is the fact that we get a very like very reliable understanding of what the flux density of these pulsars are. And this is just a very quick plot comparing the flux densities of the pulsars that we detect from our work to the literature flux density of the same sources. And given that most of them fall in that one-to-one line that I have plotted, this was a good test for us to see if we are going into some calibration issues or some way in which we are detecting flux densities higher or lower than what we expect. So we also used pulsar spectra to kind of understand if any of the spectral fits changes if we introduce these new measurements from our work. One of the pulsars that I would like to highlight is, actually I'll highlight two, this is the first, is J1312 minus 5402, in which without the point that I have pointed out, that's the point, that's the flux density from our work, it would just have a simple power law fit. However, the introduction of a low frequency measurement completely changed the fit. On the other hand, we also have pulsars that do not really change the fit at all. However, like you can see here for this particular pulsar, all of the previous detections of these pulsars were above 1 gigahertz, mainly that end of the spectrum, whereas 1 point, we only have our work that was that introduced this fit to extend to the lower frequencies. So this is one of the 14 that we detected as part of our work. So overall, we have first low frequency detection of 14 pulsars like the one that I showed in the previous slide. And imaging has actually detected a lot of the high DM pulsars that were previously missed with beamform searches for MWA VCS data. And that is just a pie chart showing the different divisions of the things that we are detecting. And so this is a very, very naive approach to understand if we are actually contributing anything to it. So in our work with this pilot survey, we were able to introduce at least 25% more pulsar detections. So in the era of SKLO, where it's coming up and it's doing some great work, eventually image-based searches in complementary to the pulsar beamform searches would actually be beneficial in improving our understanding of pulsars, not only in the terms of detection, but also in the terms of understanding their spectral behavior at lower frequencies. So this is just a summary slide. So in this pilot survey, we redetected 83 pulsars, 16 of them being only image domain detections, with 14 being the first low frequency detections. And we also did find some interesting pulsar candidates, but that's for another talk. And this kind of establishes the importance of image-based surveys. The QR code there does not take you to any scarf. It just takes you to my boring paper if you want to know more about the pulsars itself. So I'm going to leave it on this note and say that please check out. So this is where I left off as part of my PhD, but Christian has actually taken the pipeline that we have developed and made it multiple times faster and more reliable, and is doing some excellent work in eventually using that pipeline to not only detect pulsars, but also FRBs in the future. So please tune into Christian's talk today afternoon, I guess, for knowing more about the great work he has been doing, following up from this work. Thank you.
Thank you, Smita. Any questions in the room for Smita? None so far. I'll ask one very quickly to kick it off. So clearly there's the importance of the image domain searches for SKLO as well. You mentioned that Christian is making it a lot faster and more efficient. Who's going to actually be implementing this kind of technique on SKLO data?
Christian.
Okay.
So I think like it's more of a chat between the team that does SKLO processing and Christian, because I know that Christian has been has made the pipeline at least a factor of 2 faster than what I used, and it's completely GPU based now, which is great. I think he has. I'm not going to steal his thunder, so just. I don't think I can.
Writing over to Dev.
Thanks. I tried to skim the paper to try and find the detail on this, but in your pipeline flow diagram, one of the steps was peeling. Just wondering how you do peeling.
So this code actually just takes you to the pulsar sensors paper. So the paper that talks about the pipeline is the 2022 paper that we published. But as far as I remember, this was 6 years back. But if I remember correctly, the peeling was mainly done in terms of how the Gleam team used to do peeling initially, which was basically just looking at the solutions, looking at like the first pass of the image and deciding if there are any really bright sources, and you can tell to peel that source, or by peeling, I only mean it creates a mask so that that does not affect any of the imaging aspects that we are working on. So it creates a mask around the image so that all of the artifacts that you would get out of it is essentially not there. But to be honest, like we only had to do that for 2 out of the, I think, 15 to 18 observations that I processed in the 3 years. So that was only for very specific observations that we actually had to take care of once we got the final images and we were not happy with it.
Okay, cool, thanks.
Any more questions in the room or online?